In this video, I'm going to be breaking down Leetcode's Leetcode list specifically for sliding window. By the end of this video, you're going to know everything you need to know in order to ace sliding window problems. I'm Raymond. I've solved over 1,200 Leetcode problems, and I'm also currently top 3% in the world in Leetcode. Let's get into the video. Okay, we're going to start with the best time to buy and sell a stock. You're going to be given an array of prices, where prices at I is the price on some given day for a stock. We want to maximize the profit on a single day by choosing one stock that we can buy and then a different day that we can sell. We want to return the maximum profit from this transaction. If you cannot achieve any profit, return 0. And given us an example, so we've got like these values here. Best idea would be to buy on this day and then sell on this day. Right, so we want to kind of go through here and here and then get 5 as our profit for that time because we bought it for 1 and then we sold it on day 5. And then in this case, like it's impossible, so we return 0. Going into the solution for this problem, we are going to be essentially just grabbing like the minimum every single time and then calculating the profit that we can at each time. So something kind of interesting that we can do, right, is when we're looking at how this is calculated, we'll try like going through and we're like, okay, well, can we do it with 7? No, we can't. Okay, yeah, sure, let's take 7. It's the best one we have so far, right? Like out of all of our options, we should probably do 7, right? Now, interestingly enough, if we scan all the way over these, like which is the best option? Well, it's the 1, right? This 1 is going to be the best option because it's just the smallest, right, in this range. And so like if we're going to have like a 6 that we're going to calculate profit with, we should just take the smallest number like every time. And this gives us into like this observation gives us a nice hint into how we can solve this problem where, oh, okay, well, what's the best profit here? Well, it's the 1. But every single time, it's just that we just want to keep track of the minimum at each phase that we're here. And that's going to lead to us having like the best profit. There isn't really a minimum that we can like access here, but which means that we just return 0. But for this case, it's really nice that we can just kind of do this. Now we can do is like, okay, 7. And okay, so then we do the 1, we calculate profit. Oh, well, it's negative. Like, why do I want that? Okay, so then we take the 1. Now this is our best option and we can keep going and going and going and going. And so what we'll do is we're going to just code this out. So coding this out, we're going to see that we're going to have a max, call it maxi because we can't do that in Python. Now, fun fact here, right? We're doing 1 because you can't have a negative profit as our total thing, but like let's say like total profit, the total profit has to be 0 at minimum. We'll never sell for like a loss. We're not like that dumb, right? We're not that dumb, guys. We won't sell for a loss. All right, so then we're gonna say minimum so far, and then we can set this to like some super big value. We could even set it to prices at 0 if we wanted to, but doesn't matter really. It's quicker, easier to write this. So for num in prices, right, for every single number that's there, then we want to just calculate the total profit. So total profit is equal to the max of total profit. And then we're going to do a minimum so far, right? And so it's the total number minus the minimum so far. And then we just update our minimum so far, which is the minimum of the number and then minimum so far, right? And then we just return the total profit, just like that. See if I typoed somewhere. I did not. And see if it passes. It does. So again, general idea here, and that what this problem is teaching you is just that like, if you can like just notice this pattern of like, what's like the best option to buy stock? Is it the 7? How do we know that? Well, because really all we're doing is we're grabbing like the biggest number and then we're picking the smallest number to the like left of it. Like we're never going to pick 7 because we know like it's just like there is a smaller number here. And then there's like another bigger number here. That's what this problem is just going over, basically. It's kind of testing your knowledge on that. And it's a pretty famous problem, so worth knowing. That said, this is not a sliding window problem. Like I would not consider this at all a sliding window problem. Not sure why Leetcode places it here. If I were going to rank this and we were going to put this into a tier list for in terms of like sliding window problems, if we were going to rank these for like, let's say like tier list of like sliding window type problems, I would rank this in F tier. For sure. I'm not seeing like the sliding window stuff kind of happening here, but maybe I'm crazy. Maybe you guys can tell me in the comments if I'm insane, but I would put this in F tier for number 121. Now, let's get into the second problem, longest substring without repeating characters. Okay, in longest substring for repeating characters, we're going to be given some string s. We need to find the length of the longest substring without repeating characters. We can go through here with ABC, and we'll see that this is actually like the answer, because if we were to do this, it repeats. If we do this, it repeats, right? Like there's nothing that we can keep expanding out. Same with this one, repeats, and then this one also repeats. So we just don't want like non-repeating characters. Now, what I'm going to go into here is actually how do you do sliding window problems and like the general base structure of like how you can ace every single sliding window problem, right? So what we're really going to be doing for all of the sections that you guys are going to notice here, when we do all these sliding window problems, we're just going to be following like some basic formula, right? And that formula is like, okay, well, what is the window? Okay, initialize the variables, left and answer, and then loop through, right? And so looping through is really just this for our ch and enumerate s. And then, so this is the base formula that we're going to be following on every single sliding window problem. That makes it like just so easy. First thing is, what is the window? Every single sliding window problem is going to have some kind of like window, some kind of container that we're going to be having. Maybe it is a hash map, maybe it is an array, maybe it's a set, maybe it's a counter, maybe it's a heap that you can have as like that container of the elements. But we're just going to figure out, okay, what that is, right? And so in this problem, our container is going to be some type of like either counter or some kind of set, some kind of hash map, right? We want to know like what are things not repeating, so we could just keep a container of like everything that's just not repeating. Like that would be amazing, right? And so we can actually do that and using a hash map or a set. So what we'll do is we'll create our window, call it like a set, initialize it here. The next thing we want to do is initialize our variables, right? We could fill the window right here too if we wanted to, but it's not necessary. Not really like super important. If you want to, maybe you can decide. We'll initialize our variables. We'll always set them to 0. Left-hand side of the window goes to 0. And then we're just going to slowly expand to the right. And how do we do that? We just do a for loop just like this. Code's going to look the exact same as this. Have a right loop, and then we're just going to constantly expand. We're going to be adding to the window. So how do we add to a window? We do window.add, and we add the character to it. And then we need to make sure the window stays valid. Now, this can go in different orders. We can add before, add after. In this case, we can just check here and say like if window or if ch is already in the window, well, then it's obviously going to be invalid, right? Like we cannot expand to the right anymore. So like we're like, okay, add A, add B, add C. Oh, hold on, we can't keep adding anymore. Like this is the max. It can no longer, this is the longest this substring can be, right? Like we were adding. This is the longest it can be. So like, why would we ever keep doing it, right? So what we want to do is expand to the left until we can actually fix this barrier, right? We need to fix the window. So we need to make sure the window stays valid. So what we're going to do is we can change this to we can make this a while loop. This is probably a little bit ugly, but I want you guys to just kind of understand is that like, okay, while ch is in the window, then we need to remove like whatever the leftmost character is, right? So that's going to be window at left. And then we do left plus equals 1. We'll also do a check here every single time to make sure that we're in bounds. And then we can just define our in as the length of s. We just want to make sure this is always in bounds. And actually, it's not even left, it's actually right. My bad. So we just want to make sure that we're always in bounds. Take our leftmost character and then remove it. Okay, so we'll take our leftmost character, remove it, and then just keep going while this like we're kind of blocked here, right? So we need to find the A. And there could be variations where like we just don't have the A yet and that we really need it. So we'll go here, right? Break it up like we don't need this anymore, right? So like, okay, we're stuck. Make up up, increment the left pointer, go here, increment, and now we're good again. So now we can keep advancing to the right until something else happens. We'll just keep doing this. Remove, remove, remove. If there's no problem, then we add it. Interestingly enough, like we just want to add it to the end every time, and then just make sure it's valid. So this is where we're kind of getting through. So we're just going to expand the right side of the window at some point, and then we need to make sure the window stays valid, right, in this case. So sometimes you flip these steps, depends, but in this case we kind of go it this way, and then we can just run this. Cool, and there we go for this solution. Very quick, very easy, right? So just this idea of like, if you can follow this template, if you can understand what the container is, if you can understand that you just need to make the window valid, and if you can understand that we're constantly expanding the right side of a window every single time for all of these algorithms, this becomes a lot easier and a lot simpler than like trying to do things like reinvent the wheel, trying to invent Dijkstra's algorithm and all of that stuff. So that is this portion of this problem. Now let's go into the next problem, which is longest repeating character replacement. So you're noticing some things here too, right? Is that like a lot of these sliding window problems have to do with like longest. And so when you read something that says longest, or they want you to get like a longest substring or whatever, like here, longest substring, you would probably just think like, hey, this might be a sliding window problem. And in this case, you know, this one is, it happens pretty often because the idea of sliding windows that you're gonna have some kind of substring or subarray that you need to kind of just expand out. And you're generally always just going to the right in one direction. Once you hit the bounds, once it's invalid, picking up on the left side and then going until, and following that, kind of like a snail, one of those apple snails. I don't know. I think those are an invasive species. And going into this problem, so we're going to be given a string S and an integer K. You can choose any character of the string and change it to any uppercase English character. You can perform this operation at most K times. Return the length of the longest substring containing the same letter you can get after performing the above operations. Let's go through an example here. So for A, B, we want to pull out like what is like the biggest kind of conversion whenever these aren't. Return the length of the longest substring containing the same letter. And we allowed to change the characters, but we want the length of the longest substring containing the same letter. So we need to have the thing that has like the same letter, right? So here we'll say A, that's fine, and B, okay. This is kind of bad, but it's okay because we can turn a B into an A. So it actually does work, and we can keep expanding our window. Then we say A, right, which is fine, and then we say B, which is fine because we can keep expanding. We still actually, we would be at 1 here, and then we would go to 0 because we've got 2 B's that we need to convert into an A. Or conversely, we can convert 2 B's to A's. Either or here. For this one too, same thing. We can expand. Oh, we need to convert it. Okay. Well, we can't convert anymore, so there's no reason. Like we've hit our limit. Oh, and what do we do when we hit our limit? Okay, well, we just expand the left. So we're like, okay, well, we're still hit our limit here. It's still bad. Okay, now it's actually not so bad. This is actually good because now this time we're going to be converting everything into B's. If you can see this here, right? We're going to be converting everything into B's, and we can keep on going until we hit this A. And so this problem is a little bit interesting because it's going to involve us, like if you can notice this, the dominant character should be the one that everything else is converted to if we really want this to be like the longest window, which may not be obvious, but when it says that like we want the longest character of the same letter and we're allowed to convert things, but only a limited number of times, like just like that by definition, that's only going to happen whenever like it's the most frequent. And these examples are actually kind of bad too. They don't actually show you, like these are binary. So like these don't even show you, or they don't tell you anything about like, what if you have like 100 A's, like maybe 1 B, and then like 50 C's, right? But like here in this case, like the longest one is just going to be like, you know, it's going to have like 100 A's or whatever, right? Like basically we just always want the dominant one. So this one, A's are the dominant, so we always convert everything else into an A because that's going to allow us to expand the longest. And so now you can probably see like some kind of idea of like some kind of formula happening. So let's go into like another step into this, which is like, let's follow the formula to solve this, right? Which is, it's sliding window problem. We know that it says longest substring. We also just came here from sliding window from Leetcode's list. And what we're going to want to do is figure out, okay, well, like just answer these questions. What is the window? And then how do we make sure the window stays valid? These are the two questions that we're going to ask. Like this stuff, initialize variables, I can do that, man. That's easy. Look at this. Oh, we just did it. Boom. Okay, cool. We'll do a for loop. Okay, I got you. For I, ch, and enumerate. If you remember from 5 minutes ago, right? Cool. We got it. Bang, look at that. Now the hard stuff is how do we know when what is the window and how do we know when it's valid, right? So what is the window? What is going to be this container? Well, if it's not appearing, like this is not a heap, it's not an array, it's just going to be a hash map, like out of these options, right? Like, and what I mean by that is that the things we want to store is how many characters are occurring, how many times each character is occurring. So is A occurring 10 times in our window? How many B's do we have? Do we have 5? Do we have 2? Do we have 1? We're also going to want to keep track of K. How many K conversions have we used, right? This is like the thing that allows us to convert them. But we just need to know the characters' frequencies on a given window. Like for this, how many A's are there? How many B's are there? In this case, we know this window is invalid because we have 4 A's and 3 B's. 4 A's, 3 B's inside this window. And our K is 1. Like it's just no go. It cannot. So this is going to be your window. Window is equal to, and we can call this a counter. Alternatively, you can make this a dictionary, right? As a hash map like that, but why would you want to do that when we can count? Counter's just better. Okay, now the second thing is how do we know when our window is invalid? That's the other big question that we need to ask here. And our window is invalid whenever we have just too many. We take like the dominant one, in this case 4, and then we count and see like whenever these, the most frequent ones, eclipse our K, because then we can't convert them. Then they're just like, we know that's bad. So that's exactly what we're going to do here. Okay. And so what I'm going to show you guys really quickly is just like, okay, like what is it when it's invalid? Well, it's when all of the other ones are greater than K. So then we're just going to do our same thing, push it left, push it left, push it left, grab the leftmost character, increment, and then let's repeat it. Let's figure it out again. What's the most common character? What are the other differences? And just keep going, keep going, keep going. We're also going to be expanding the right side of the window, which should obviously be like we take our counter and then we add it. Now in this case, the counter, like this is called like, this is called C, but like it's our window, right? So C is our window. Add it to our window and then calculate if it's valid. Get the most common character, take everything else that's not the most common character and just keep on going. So there's a more optimal way to do this, but to get you like just understanding like kind of like this idea of sliding window, that's what we're doing. So this pass is very, very slow because there are more optimal ways, but for checking if the window is valid, as opposed to calculating the sum every single time, we could just keep the sum as a variable, add it, less, decrease from it, but still solid. So that is how to do this problem. And then we'll move on to the next one. And now we're going to go into permutation in a string. And I just realized I forgot to rank these two problems. So for this one and then this one, I would rank this one a 10 out of 10. I like it for a beginner. I would say it's essential to do this. Number 3, Leetcode problem number 3, S tier, for sure. Very good beginner one. This one I don't like because it feels like it's a little too extreme with this idea of like, it feels more complicated checking if the window's valid. I don't like that a whole lot. So I would probably say this is like B for learning as a beginner. Maybe it's a solid problem. It is sliding window and you'll learn something for sure, but I kind of wish there was just something easier where you didn't need to track like this. This kind of thing is probably confusing to people, even, yeah, especially for a beginner. But so let's go into permutation of a string 567. Given 2 strings S1 and S2, return true if S2 contains a permutation of S1 or false if otherwise. In other words, return true if one of S1's permutations is a substring of S2. So again, we've got things of substrings. This is again going to hint at sliding window. I mean, mostly just because everything's connected, so you can probably just like expand and de-expand. But we have another thing here happening, which is permutation. Like, okay, well, what is a permutation? Leetcode's very nice, and it gives us a definition. It's a rearrangement of all the characters. So kind of like an anagram. If you guys have done those problems, if you remember what anagram is into this problem, group anagrams, valid anagram, we're getting something that's basically an anagram. And going into this problem, right, so we'll have an AB, and we want to see, is there a permutation of AB inside of here? Oh, there is a BA. And so we go through it, and we return true. Sorry, we return true because we see an AB and then a BA. It does exist, which is a permutation. And same thing here, AB is not here. There is no substring of AB. Okay, so going back to our template here, let's go back to our template. Copy and paste this thing. Another question, right? What is our window here? What's happening? And so let's go back to our window here. What's happening? What does this mean? How do we know like what this permutation is? Well, one, this is using permutation. If you know in anagrams, or if you remembered, what we're going to be doing is realizing that in anagram or permutation, we can actually just count like the number of like occurrences of them, because like they have just the same characters. Like that's really important here, is that our window needs to have the same characters. So let's say we have like some window like this, like there are 2 A's and 1 B. Like this is going to apply to all permutations. So BAB is an anagram / permutation of BBA and so on. So we can convert these into like some kind of collection like this, which this is obviously, like you've seen this before. You saw it like 5 minutes ago, but this is a counter or a hash map where we're going to be counting the number of occurrences and then seeing if it's good using this kind of like idea. So what we can do is take an AB, convert it into something like this, right? So we say A is 1, B is 1. And now that we have these converted, we can just check, hey, does anything else match this? And what else is going to match it? Everything else of size 2, because we know it needs to be the same size. So everything else is size 2. So we'll go here. Is it? Nope. 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 Yes, it is. That's how we know it's an anagram. We go through it every single time of the sizes of the same length. So we're going to have a window of some size, and we're just going to keep going through. Now this represents a slightly different variation of this, because we're not going to be like, we're expanding the right side, yeah, but like the window is this actually, and it's never changing. We're just going through. So this is a unique situation. It's also like useful to know, but like this case, we're not actually checking if it's valid. We're just comparing windows, comparing a window and a window. So in this case, we'll have like window is equal to counter. And then like our target window, we can say is equal to the counter of S1. So very quick in Python to just count this up. And then we'll have our window here. And this is where I mentioned that we need to fill the window, but you know, maybe it's not necessary, because we could just say like if like right minus left, like +1 is less than length of S1. Well, then we just add to the window. And then if it's greater than, then we just remove it from the window. It's like S at left plus equals 1, window at leftmost character minus equals 1, and then we have to always check if it's needs to be deleted. Then we just delete it, honestly. So then we delete it. So we're gonna add to window while not equal, or just add to our window while valid or while invalid. And then we're going to remove left part from window and add right part. So then we'll go here, add it, and then just check if they're equal. If window is equal to target window, return true, and then return false. So what we're gonna have here is we're gonna define our window, create our target window, which we're gonna be using to compare it. Initialize our left and right. Again, this is like kind of useless because this is a different variation of a sliding window problem, I guess you could say, where we don't really, like we need the left for sure, but we don't need the answer. We're not returning an integer, we're returning true or false. So we don't actually need that. We'll loop the right-hand side, constantly expand out here, right? So we'll expand, and then if they're ever equal, we return true. If they're ever equal, return true. And then we just remove the leftmost part, right? So you can understand that if we don't want to keep growing beyond a certain limit, we do want to limit this to 2, and then keep growing, kick out E, add in D, and keep going. Okay, and then what we'll do is submit it. I did have to make a change here so right minus left is just less than the length. And there we go. We get this accepted. Actually, just move this here. Now, curiously, there's maybe a slightly better way that you can do this. So here's a slightly better way you could probably do this, where you just fill the window in beforehand, and then we go into just expanding. Again, I prefer using R, but we just check, and then we can just pop from the left because we know it's filled, and then go from the right. But this just prevents us from needing to do like that, this if statement stuff from here. So you get your choices. I think this is like a fine kind of way to do it, and it's a little bit slightly different, but we're just moving from the left, as I said, and yeah. Overall, I think this is pretty important actually. So if I were gonna do a tier list, I would actually put this one right here at the top as like definitely important to do, because this is a different type of pattern than the ones that worked before. Okay, and now our journey into sliding window is almost over. Hope you guys are learning a lot. I sure am. Not really. This is not helpful at all, but hopefully it's helpful for you guys. So if not, then I won't do this anymore. And if you guys want more like type of like solutions and things like that, let me know in the comments. If not, then I will definitely not do anything like this ever again. So let's go into number 76, minimum window substring. So given 2 strings, S and T, return the minimum window substring such that every character in T is included into the window. There is no such substring, return an empty string. So the minimum substring of S such that every character of T is inside of it. So we need the minimum here. So here is A, B, C. This is like pretty big. Now let's play around again with the sliding window stuff. Expand to keep the same kind of idea, right? Like I could write this out. I don't know if I need to write this out again, but like just go back in the video and look at those 2 questions. 1, what is our window? And then number 2 is how do we know it's valid or not? So it's pretty obvious here. Is included in the window, so it's every character of T included in the window. That is when it is valid. We know the window is valid when every character of T is inside of it. Okay, now how do we store those? What are we going to be using? In this case, once again, it's a hash map. Not super, different, but not always going to have a hash map. But in this case, it's another hash map. So we can store everything just like this. If you saw what I was doing here, store the characters such that every character of T is there. And we just keep going, right? So A is 1. Okay, cool. We have this many. And we're just going to be checking, making sure it's valid. And okay, should be that. Okay, cool. Yeah, and okay, so that is that, right? ABC needs to be here. So then what we can do is just expand. It's invalid. Expand while invalid. Pick up everything. And then once it's invalid, let's try to fix it. Like, let's try to shorten it. What if we just make it shorter? Is this invalid? Yeah, it is. Okay, cool. Then I need to expand. Expand. We need an A. We're missing the A. We need the A. Oh, we have it now. Okay, now let's decrease. Decrease, right? Like, okay, we're in here. Nope. Here, this is it. This is the best one that we can do. Because then it becomes invalid. And then we need to keep expanding. right? But we can do this kind of idea and eventually we'll decrease, decrease, decrease until we're here, right? And it's valid. So if you can see this, it's a little bit of flipped on its head of like, just a slight variation of what I was talking about, but like we declare our window. What is our window? Oh, well, our window is yet again a hash map. We can use a counter. We're going to declare left. We're going to have our answer because we want, actually we want to return like the length. So our answer is not going to be an integer, but it's going to be like some kind of string. And minimum length so far. You can say it's like math infinity. Let's keep track of the minimum length too, right? So we can have our answer nice. For our ch and enumerate t or s. We'll go through, let's add to our window, window.add ch. While, how do we know when it's invalid? Window not equal to target window, right? What is target window? Okay, well, target window is just t. We did this before. Counter t, just like that. And then while it's not equal to the target window, or while it is equal, let's shrink it. Right, a little bit different, but like while it's valid, we actually are going to shrink it. So leftmost char, s at left is equals 1, and then window at leftmost char minus equals 1, remove it if, then we just delete it. Oops. Go here, go back, here, here. While it's 0, go through there. And then what we can do is say if minimum length so far is less than or greater than r minus left plus 1, should be the size of the window, then answer is equal to s from left to right. And then we return the answer. So this is very generally like the kind of idea. I might be off by 1 here, but we're going to want to like just split the string if it's not, and then also reset this. Just like that. So we expand, 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 add it, add it, add it, add it. While it's invalid, we shrink it. Shrink, shrink, shrink until we get there. So let's go ahead and look at this. Okay, one thing I want to call attention to is I need to add this left minus right, I believe. So that'll make it a little bit better. So let's run and see what happens. Okay, so there is no add. So we have to do this. Little syntax issue. Okay, so going into the solution of this problem, right? So we're going to declare our window, and then this is going to be our target window, which we did very similar into the other problem from earlier. Then we're going to create our window here, have our answer. Now the answer returning is not an integer this time, it's a string. So we're going to be keeping track of that, and then also keep track of the minimum length of the string so far, so we can know whether or not we need to replace it. We'll have like the required kind of like characters that we need, and then we're going to see like how many have we actually like built so far, like how many are meeting this criteria of this, because we can't actually compare window and window because this is going to have a ton of characters that this window is just never going to have. But we need to see, are those characters actually met? Add to our window, same thing, do a for loop, right? If you remember, again, the formula. Check, is this character in the target window? Do we missing some things like in the window? If we're not missing anything, okay, we're done then. Let's add it. And then we just go through while this is like isn't equal, let's just keep going. Let's add it, update it, and let's shrink it. And then here, we're just gonna check, is that leftmost character like less than now? Is it not formed anymore? We'll reduce it. And we'll just keep doing this over and over again, shrinking, shrinking, shrinking. And this will give us a nice answer. So that is this problem a bit more complicated for sure, right? We're doing several things, different things here. We have a minimum thing here. We're keeping track of the string. Also, when it's invalid, it's a little bit different because we're also need to check like whether or not it's formed. But if you understand these principles, it becomes like pretty easy to understand this. So that is that for this problem. I would rank this one, we're going to a tier list. I probably put it as B, honestly, like for a beginner, but it's pretty important for sure. I would say maybe A, actually, because it's more important than that other one, for sure. 76, but like that's stretches out and make it 76. Hard to read, but you understand what I'm saying, I think. And finally, we're going over the final problem, or as some may say, like Elon Musk, the final solution. So what we're going to be going through here is doing sliding window, finding the sliding window maximum. You're going to be given an array of integers and a sliding window k, moving from left to right. You can only see the k numbers in the window. Each time the sliding window moves right by one position, we need to return the max sliding window. What is the maximum number that is in here? Again, let's follow the same rubric. What is going to be our window? When is the window valid? In this case, the window is always sliding, so this idea of a valid window doesn't ever come up. The real question is like, just how can we get the max from this window, right? So it's like, okay, well, what's the max here? It's a 3. So we put a 3 here. What's the max here? Oh, it's a 3 still. Okay. Now it's a 5. Now it's a 5, 5 or 6 actually, and 7. So let's probably think on, need to think about how to do this. It's something with pulling the max. So using what we've learned, there are several ways that you could probably think about doing this. One way is that we do the same thing that we did before with this, is that we just count how many numbers that we have, right? So we've got 3, we've got 2 of them, 1, we've got like 1 of them, whatever. And then we just say like, okay, let's go through all of these and then just pick out what it's the biggest one. And that's our answer, right? So this ends up being like O of like the numbers. Now the numbers can be actually pretty big though. So this isn't a good solution. There's a better way for sure. Secondary solution that's a little bit bigger or a little bit better is that we just go through once and then count however many biggest ones that we have. And then we already know, and we also keep track of what's the biggest. So we keep track of like, what's the max so far? So 3. So instead of having to search through everything, we just build it and then establish this. And then whenever we like eventually like start killing it, so it's a 1, it's a 0 because we end up obviously shifting to the left at some point. Well, then once it's 0, then we kill it and then look for a new one. Search, and then we do a search for the new one. That is another option. Now the final option is something that I mentioned before, which is that like whenever we're solving these problems, we need to pick the container, right? We don't need to use a hash mount. We can actually use a heap. So what if we had the biggest number, our container, what if our container was just a heap? So we keep adding like a 3, we add another 3, and then we add like a 1 or whatever, and this is our heap. And now we always know what the maximum number is. And anytime our window, like this is the unique part, right? Which is like, okay, well, like, yeah, sure, let's use a heap, but like, how do we know how to kick out this 3? Like, that's really hard, Raymond. How do I know when to kick it out? Well, we can also store the indices. So we can say a 0, a 1, a 2, whatever. And when our window, or when we're like too far out, we need to kill this and then find the next one. So in login, we can just start bubbling basically, and it will bubble immediately, bubble like the next best one. So this is how you can do it. Don't think there needs to be any other explanation than that. I mean, if you don't know what a heap is, like this is one of those problems where it's like, I mean, if you don't know what a heap is, it's a data structure that allows you to keep track of the max every single time. So it's a tree structure like this, and you can actually do it. But anyways, this is out of scope for this problem. If you want the optimum solution, you would use a heap as your structure, or use any of those other 2 methods that I mentioned here, which I'm sure would work, right? But this is just more optimal. So we're going to show the heap solution, actually, because why not? Okay, and with this, we can say, okay, well, there's a heap. We add to our heap. Answer here, here. And then we'll constantly move towards the right, adding numbers. But before we add the numbers, let's make sure our heap is valid. need to make sure our window is valid. It's only valid if this minimum is outside the window, so that we can start canceling them, and then finally we'll add and push all of those. So that is the solution, and hope you guys enjoyed this. Again, you can let me know if you want me to do more videos where I just go through breaking down like how do you do all of like the Leetcode list problems. You know, we could make a full 10-hour video series of going over all of these, but that is all. And if you're interested, if you're still watching, I also have another video where I cover all of the arrays and hashing problems, and so it's about 1 hour long. If you want to see me solving these live, you are completely free to, and I'll see you in next video.